So I'm Paul Lipman, president of quantum computing at ColdQuanta. We're a pure play quantum company. And so what we do spans the spectrum from developing and manufacturing products that we sell to a variety of other quantum companies, everything from glass cells for trapping and manipulating atoms, all the way to systems for creating and working with Bose-Einstein condensates, which I'll talk about a little bit later. We have an advanced research group that does over-the-horizon funded research in quantum sensing, everything from precision, navigation, and timing to RF sensing, and we even have quantum systems that are operating today on the International Space Station. So where many people here in the ecosystem talk about putting quantum on the cloud, we've actually gone one better and we've put quantum above the cloud. So all of that technology, that IP, that expertise supports the development of our cold atom quantum computer, which we believe is the most pragmatic path to building large-scale quantum systems. So at ColdQuanta, our qubits are individual atoms. We actually trap them in this cell right here. So this is the heart of the QPU. We trap the atoms and we then cool them down with lasers to operate at microkelvin temperature. So this is millionths of a degree above absolute zero, but we're doing that in a device that's operating at room temperature. And we're using cesium for our qubits, and cesium, the clock states of cesium, are the international timekeeping standard. So if you think about GPS, for example, or trading networks, all of that relies upon atomic clocks, which are using cesium in most cases. So extremely stable quantum states, extremely long coherence times, but our gate times are measured in just a few tens of nanoseconds. So that ratio of a long coherence time with fast gate time enables the development of deep quantum circuits. So in order to build large-scale quantum systems, and we've heard a lot about this at the conference and in various presentations, it's really a combination of three fundamental components, at least from a hardware perspective. One ultimately will require a large number of qubits, and obviously those have to be good qubits. But in the case of atoms, these are neutral, and so we can pack them very close together in an array. We use a 2D array, conceivably over time, a 3D array, and these atoms are just a couple of microns apart. So the cell you see here could hold tens of thousands, conceivably as many as 100,000 qubits, again, operating at room temperature. It's a very inherently scalable approach. And then the route that we use for entanglement is through Rydberg excitation. So the atom is highly excited, and that Rydberg excitation has a large effect across the array. So as opposed to, say, superconducting qubits where you have to engineer your connectivity, maybe you get a 2-to-1, a 3-to-1 connectivity, we're essentially doing software-defined connectivity. And so we can entangle qubits on the array conceivably up to connectivity of 50-to-1 to 100-to-1. So that opens up a range of possibilities for error correction and algorithms that are simply not possible with other modalities. And then ultimately, we're seeing very good progress in 2-qubit entanglement fidelity, and this will easily get to 3 nines and beyond over time. So as you put these three together, importantly, what is the fundamental limitation here? It really is around the lasers and the optics. And so we get to leverage the billions of dollars that are being invested on a global basis in the optics industry, in photonic integration, that serves the purpose of enabling us to build these very large and highly addressable qubit arrays. So at the same time as we're scaling up in terms of algorithmic complexity, in terms of the power of the QPU, we'll be scaling down in terms of form factor. As I showed you, the cell here is essentially the heart of the CPU. It operates at room temperature, and the rest of the QPU today is lasers, it's optics, it's electronics, all of which we can shrink down over time, and we have experience doing that at ColdQuanta. As I mentioned before, we took a system that was a large optics table, we shrank that down to something that was then deployable and got sent into space and is operating today in low Earth orbit. And our goal over the next several years is to do the same thing with the QPU to eventually have the point where really it's just a couple of 19-inch rack-mountable units. And that will open up a range of new use cases. You can imagine a QPU actually physically co-located with the classical workload to improve fidelity, to improve cybersecurity, in a satellite, as a node, in a quantum network, and even on the desktop in your lab or in the office. So every journey starts with a first step. Ours is the introduction of our first quantum computer, Hilbert, which we'll be releasing early next year. That will scale to 100 qubits. Initially, will be available through our own cloud platform. We announced a relationship yesterday with Strangeworks, and we're looking at the other cloud platforms over the remainder of the year. Initially available with support for Qiskit and Cirq, and so this will be a general purpose gate-based quantum computer based upon the cesium atom. But we're not waiting actually for the release of Hilbert to announce important milestones. We recently conducted a really interesting project with Riverlane, one of the leading quantum algorithm companies, and the University of Wisconsin-Madison, Professor Safman's lab, where we believe for the first time ever, a multi-qubit circuit was executed on a cold atom quantum computer. And we'll be releasing a paper on the archive later this month containing the details. This was part of a green battery project, but a really important milestone for us at ColdQuanta. We believe an important milestone for the cold atom community as a whole. So looking further ahead, we're really firm believers, as I've said before at ColdQuanta, that this industry gets moved forward through collaboration between the hardware vendors, between the software and the algorithm developers, and the early adopters who are really pushing use cases. And so as we work towards, over the next several years, reaching 1,000 qubit scale with very high connectivity and high gate fidelity, we're very keen to partner with players in the software industry and early adopter customers who want to work together to explore the possibilities that cold atom quantum computing can unlock. And this path to 1,000 qubits, this is not just kind of a pipe dream on a PowerPoint chart, but already in the lab today, we're trapping over 400 atoms in an array. We'll soon be announcing the achievement of 1,000 atoms trapped in the array. And we're investing very heavily behind the enabling technologies to turn that into a QPU at that kind of scale. The beam steering, the error correction, the atom transport, these are all fundamental technologies that are required to realize the dream of very high qubit count, very high connectivity, and very high gate fidelity, again, in a system that is this size and operating at room temperature. So I've talked so far about Hilbert, our computer, and our path to building large-scale gate-based quantum computers. I want to spend a few minutes talking about our other cloud service called Albert, which is a unique service for quantum matter emulation and dynamical system development. So Albert is the world's first and only quantum matter system on the cloud. It's the same core technology that's operating on the International Space Station in low Earth orbit. And the best way to think about this is as software-defined ultra-cold matter. So when you think of superconductors, you're talking millikelvin range. When you're talking about Albert and other cold atom computers, you're talking microkelvin range. Albert is operating in the nanokelvin range, so billionths of a degree above absolute zero. Again, still in a system that's operating at room temperature. And when the atoms, typically tens of thousands of atoms in Albert, reach that temperature, they condense into a state of matter called a Bose-Einstein condensate. Essentially, the atoms take on a single quantum ground state. They're acting really as a single quantum object. And we can then define, using software and paint, a variety of complex potentials on that matter that enables us to do sensor development, gravimeters, graviometers, accelerometers, and we have some early adopter customers that are looking at using Albert for life sciences and material sciences for truly emulating thermodynamic dynamical systems in a way that can't be done with any other kind of system. But the real business benefit here for Albert is to radically reduce the time to market and the cost for doing this kind of work. So it would have been in the past, you would have had to spend millions of dollars over several years, hire an army of grad students to do this kind of work. And now when Albert launches commercially at the beginning of next year, you'll simply be able to log on via the cloud and do your emulation and simulation right with the Albert system in a very straightforward way. So I'll finish here by giving a couple of examples. The first, the development of a quantum gyroscope, and this is based upon work we're doing in our office in Oxford in the UK. So with Albert, we could paint a ring potential, put the BEC into a ring, coherently split that BEC, and because matter has mass, obviously it's very sensitive to inertial forces, and we can then measure the interferometry pattern of that BEC to develop a highly sensitive gyroscope, orders of magnitude more sensitive than a laser ring gyroscope, but doing that with a system that's based on the cloud. So not having to stand up equipment, not having to hire a team, not having to spend years to develop and tune and test, but really doing that in real time and getting results in just a matter of minutes. The other example is a really interesting one. So in this case, we're creating essentially a resonant cavity with this ultra-cold matter. So this could be used, for example, to create a linear accelerometer, but we have some customers in the academic world who are looking at this as a potential way to measure gravitational waves. So if you think about the LIGO observatory that's using laser light to measure kind of tiny changes in distance as a gravitational wave moves through the environment, doing that with matter, well, actually matter has a much smaller wavelength than light. So conceivably, one could use this kind of system as a way to create a much smaller, more stable, more robust, and ultimately more sensitive gravitational wave detector. But that's kind of way beyond my technical knowledge, so I'll wrap up there and happy to take any questions. Also, feel free to come find me at the conference or contact me either by email or by phone. So thank you. Any questions? I think we have time for one question. I would say I give this away as a prize for the best question, but that's not going to happen, but please ask away. Okay, well, thank you very much.